Okay guys, welcome to another lecture. So we have already discussed about the relativistic momentum, and as this material has been already circulated, and I will quickly move through these notes. And now I will be discussing about the relativistic force, work, kinetic energy, and eventually I will be discussing about the energy momentum relation. So all these concepts are defined by analogy with the corresponding Newtonian versions. Thus the relativistic force is defined as F, that is rate of change in the momentum is called the force, then the F is defined by dp by dt. Now a definition which reduces to the usual Newtonian force at low velocities, this force will do work on a particle, and the relativistic work done by force F during a small displacement dr is once again defined by analogy as, we know that dw is equal to F dot dr, that is work done, force into displacement. The rate at which F does work in them is then, that is the kinetic energy, that at which rate this is working, that is the P. I am defining the some parameter P is equal to dw by dt is equal to F of dr by dt, and dr by dt simply it is a velocity. As we can introduce the notion of relativistic kinetic energy by viewing the work done by force F as contributing towards the kinetic energy of a particle. So this P I could define that rate of change in the kinetic energy dt by dt, capital T by dt is equal to F dot of u, where T is a relativistic kinetic energy of a particle. We can write this last equation as dt divided by dt is equal to F dot u, because this is dot product is associative, then I could write u before this F, and this F I know from equation number 19, this dp by dt. So this P is now here is a relativistic momentum. As we know that the relativistic momentum is P is equal to m naught u divided by under root 1 minus u square divided by c square. Now simply once you are taking the derivative of it, then so u is already there, so this is m naught u of dot du by dt divided by 1 minus u square divided by c square. Just first you are taking the derivative of this u, then the second time you are taking the derivative of under root this one, then you finally will be ending up this m naught u is this m naught and u dot this u, because once you have this u already there, then you have in this u, then this under root 1 minus u square divided by c square, then you simply it is minus 1 upon 2, then under root 1 minus u square or c square, it's a cube, then you have this minus term already, you minus term over here, then this is minus term cancels out, and this 2 factor is cancelled out because 1 upon 2, this is coming, that power is minus 1 upon 2, then this 2 cancels out, then finally you have this relation. But we know that u of du by dt is equal to u of du by dt. Then both are the du, and it's a time derivative of the velocity, and its the velocity will be having the same direction. Then I could simply write this u of du by dt. So once you have this relation, then one can write this dt by dt is equal to m naught divided by 1 minus u square c square plus m naught u square divided by c square under root divided by under root 1 minus u square divided by c square of q, u of du by dt. Or simply, once I am taking that the common outside is m naught divided by under root 1 minus u square divided by c square is the q, then inside what we have, this whole term I am taking out, then this 1 minus u square divided by c square, it's e square, then it's a root, then you have this 1 minus u square divided by c square over here, then this u square divided by c square over here, then u of du by dt, and then finally du by dt is equal to m naught under root 1 minus u square divided by c square, it's a cube, and this cancel out, then you have u of du by dt. Or So I could write this expression in a derivative form. Du by dt is equal to d of t of m naught c square divided by 1 minus u square divided by c square. Once I will take a time derivative of this equation, I will be getting the same one. So once I will take a time integration with respect to t, then this capital T is equal to m naught c square divided by 1 minus u square divided by c square plus sum of the constant. And this constant, by requiring that this t is equal to 0 for u is equal to 0, suppose t is equal to 0, once I am putting t is equal to 0, u is equal to 0, then I have this constant is equal to minus m naught c square. Then putting that constant in this equation, then I have this capital T is equal to m naught c square divided by 1 minus u square divided by c square minus m naught c square. So interestingly, if we suppose that u is very less than to c, we can find that by the binomial expression. We know that this 1 plus of x raised to power n is approximately 1 plus of nx if x is very less than to 1. In the same fashion over here, this 1 upon under root 1 minus u square c square, I could write this 1 minus u square divided by c square, it's raised to power minus 1 upon 2. If we will expand it up to the first term only, then 1 plus of u square divided by 2 of c square. So that putting this equation, this condition in the equation number 26, then t is approximately m naught c square, and expanding this one 1 plus u square divided by 2 c square minus m naught c square. This m naught c square term cancelling out, then you have this m naught c square cancel out, then finally you have a half of m naught u square, which as should be the case in the classical Newtonian expression for the kinetic energy of a particle of mass moving with a velocity u. Now this is a limiting case we have already achieved. Now once we have defined this kinetic energy T is equal to m naught c square divided by under 1 minus u square divided by c square minus m naught c square. Now we'll be defining that total relativistic energy. Now we'll be defining that total relativistic energy. So now we can define a quantity E by a term T plus of m naught c square is equal to, then T is m naught c square divided by 1 minus u square divided by c square minus m naught c square, then m naught c square cancels out. Now this quantity is known as a total relativistic energy of a particle of rest mass m naught. It is good to define such thing, but apart from the neatness of expression, is there any real need to introduce such a quantity? There is a question that why we exactly defining in such a fashion that in order to see that the value of defining the total relativistic energy, we need to consider the transformation of momentum between the different inertial frame of reference S and S prime. So to check whether my total relativistic energy is having such form or not, to represent that we have to consider the transformation of the momentum between the two different inertial frames S and S prime. And once I am defining this S and S prime, it just this S prime is moving with a velocity of Vx with respect to the inertial frame S. So to this end, consider that this just we are considering this px component only. So px is equal to, I have this m naught ux divided by 1 root 1 minus u square divided by c square, where this u square is ux square plus ui square or uz square, where u is the velocity of a particle relative to the frame of reference S in term of the velocity u prime of this particle relative to the frame of references S prime. We can write, because the velocity transformation, if you remember this equation number 6 in the previous lecture, Then you have this ux is equal to ux prime plus vx divided by this uy with this relation and uz with this relation. I am representing with the help of this equation number 32, and having that this gamma is equal to 1 upon 1 root 1 minus vx square divided by c square. Once you will be doing very tedious algebra, and I will be defining this term under root 1 minus u square divided by c square. So once you will be defining this under root 1 minus u square divided by c square, now putting this value of u square from equation number 31, that is ux square plus uy square plus uz square. The value of ux square, uy square and uz square you are putting from equation number 32. Then you will end up with a after very exceedingly tedious algebra, you will end up this 1 minus u square divided by c square is equal to under root 1 minus u prime square divided by c square into under root 1 minus vx square divided by c square divided by 1 plus ux prime vx divided by c square. Now once you define this equation, once you have this relation, now with the help of equation number 32, 33 and 34, 32, 33, 34 means what I am talking this 32, 33 and 34. Now what I am defining that this px, now with the help of these equations we are putting in equation number 30. So once I am putting the value of in equation number 30, this px, I have this px is equal to m naught ux divided by this one. The value of 1 under root 1 minus u square divided by c square, we have already find this one, and this ux I will be putting from this equation number 32, that ux is equal to ux prime plus or bx and divided by 1 plus ux prime vx divided by c square. Once I will put these values, then I have px is equal to m naught ux prime plus vx divided by under root 1 minus u prime square divided by c square into 1 minus vx square divided by c square. Now I am separating this term. This I know this what under root 1 minus vx square divided by c square. This is 1 upon 1 minus vx square divided by c square. The root is gamma. I take in this gamma is outside. Then m naught ux divided by this 1 minus u prime square divided by c square plus vx of m naught under root 1 minus u prime square divided by c square, which we can readingly write as px. I could write this px is equal to gamma this px prime, because now my p, if I am defining, we know that this px is m naught ux divided by 1 minus u square divided by c square. It means that this px prime must be equal to this p naught ux prime divided by under root 1 minus u prime square divided by c square. Now I am putting that is the px and this is the vx. Now this m naught divided by 1 minus u prime square divided by c square, that is total energy E we have represented. This total energy is m naught, we have m naught c square divided by 1 minus c square divided by c square. Then in place of that one, once I will divide with this c square, then I have the same value, this m naught divided by 1 minus u prime square divided by c square. Because I have this velocity is u prime, then we are putting that is u prime. It means that this E prime and px prime are this energy and momentum are measured in the frame S prime. So this SE prime is appearing a total energy of a particle as measured in S prime. A similar calculation for a Py and a Pz can be done, and obviously we will be getting that as because these are the orthogonal components. This Py will be appearing this Py prime and the Pz equal to Pz prime. While for the energy we find that once I will be finding that energy, so E is equal to m naught c square divided by under root 1 minus u square divided by c square is equal to m naught c square. That again putting this value of this 1 minus u square divided by c square from equation number 34, from just putting the value of this one in this relation, then you have this relation. So again we are expanding it. I'm taking this term outside, it is a gamma, then m naught c square divided by 1 minus u prime square divided by c square corresponding to this 1. And then another term, this m naught ux prime vx divided by this quantity. And because c square is over here, then the c cancels out. However, this c is appearing with this 1. Again, this E, again I could write this energy E is equal to this gamma. Energy gamma, this E prime, this is the E prime, and it's the Px prime and the Vx. Now these two equation number 35 and 37 are showing that how this momentum and the total relativistic momentum are measured from the two different frame of references S and S prime. So now consider a collision between two particles 1 and 2. Let the x component of the momentum of the two particles be p1x and the p2x relative to the S. Then the total momentum in S is defined by. So now once we have these two relations, this px in term of px prime and the E prime, and this E in term of E prime and this px. If you look at these two relations are similar in a form, mathematical form, as we had the Lorentz transformations. Now we will be checking that the momentum in a frame of reference S. Suppose the two particles having the x component p1x and p2x relative to S, then the px component I could represent this p1x plus p2x, where px is by conservation of the relativistic momentum, a constant, that is the px stays the same before and after any collision between the particle. However, if I will be writing that is p1x plus p2x with the help of this relation, with the help of the 35, means with the help of this equation, then p1x and p2x, I'll be writing that is p1x prime plus vx of E1 prime. Then so I will have the relation p1x plus p2x is equal to gamma p1x prime plus p2 prime plus gamma this E1 prime plus E2 prime of Vx divided by c square from equation number 35. So where this P1 prime and the P2 prime, P2x prime are the x component of momentum of a particle 1 and 2 respectively, while E1 prime and the E2 prime are the energies of a particle 1 and 2 respectively. All the relative to frame of reference S prime. Thus we can write this P of x is equal to this Px is equal to gamma of Px prime plus of gamma E1 prime plus of E2 prime Vx divided by c square. Once again, a momentum is conserved in all inertial frame of reference. We know that Px prime is also a constant. If this is a constant, this must be the constant. It shows that we conclude that in equation number 40, this E1 prime plus E2 prime must be constant. So what we are saying at this juncture, this P1x, that is before the collision, that is a P1x plus of P2x, we are saying that it is a constant. And the momentum is conserved in all the inertial frame of reference. We know that this Px prime is also constant. That is the same before and after the any collision. Means this Px prime, that is the P1x prime plus P2x prime. This is a constant. From this equation we conclude that this E1 prime plus E2 prime must be constant. That is the total relativistic energy in S prime is conserved. But since S prime is an arbitrary frame of reference, we conclude that the total relativistic energy is conserved in all frame of reference. Though of course the conserved value would in general be different in different frame of reference, but that must be the constant. Since matter can be created or destroyed, we generalize that to read the total relativistic energy of a system of particles is always conserved in all frames of reference, whether or not the total number of particles remain a constant. It means that whether this number of the particles remaining the same or not, but the total relativistic energy remaining the same. It means that suppose the two particles are sticking out, or the one particle creating the two particles. In both the cases, the number of particles are not constant, but the relativistic energy must be constant. Thus, we see that the conservation of relativistic momentum implies conservation of total energy, total relativistic energy in special relativity, whereas in a Newtonian dynamics, they are independent conditions. So if you look at this, momentum and energy do not have, these are two independent parameters in the Newtonian dynamics. However, in the special theory of relativity, due to the symmetry relation of space and time, we have a dependency between this relativistic momentum and the total relativistic energy, because this relativistic momentum implies the conservation of total relativistic energy. Nevertheless, both conditions have to be met when determining the outcome of any collision between the particles. Just as in Newtonian dynamics, the equations representing the conservation of energy and the momentum have to be employed. So a useful relationship between energy and a momentum can also be established. Its value lies both in treating collision problem and in suggesting the existence of particles with zero rest mass. So the starting point of this expression, we had this total relativistic energy is equal to m0 c square divided by 1 minus u square divided by c square. Then the c square, I'm just squaring both the sides. You have this one, m0 square c4 divided by 1 minus u square divided by c square, and taking that m0 c4 and just adding 1 minus u square divided by c square plus u square divided by c square. Then once you are taking this is inside this whole term, then this is cancelling out. Then you have this m0 c square plus m0 square c4 divided by 1 minus u square divided by c square into this u square divided by c square. Then finally you have m0 square u square divided by this term. But since I know that this m0 square this m0 u divided by 1 minus u square divided by c square, that is a momentum. So this p square, I could write this p dot of p, that is the m0 square u square divided by 1 minus u square c square. So in place of this one, I could write this p square. Then finally I have this total